Hello. Now, continuing our work with graphs of cubic functions, we're going to go back to GeoGebra. And we have our negative cubic function here. I know that it's a negative cubic function, both because I can see the equation, and also because I can see that it is starting off when x is negative, my y values are positive, and then as x gets more positive, as the cubic part becomes the most important part of our function, we end up with negative y values. So I can immediately see that this is a negative cubic function because of its shape. And what else can I read about it here? I can see that it crosses the y-axis. Its y-intercept is going to be at 2. And I can see that that means that the constant on the end of my cubic is going to be 2. So the same thing that we knew about our quadratic functions, that the constant on the end give us the y-intercept, is still true with cubic equations. And I can see that I have one root here at x is equal to 2. But this is a cubic equation. I would expect to have 3 roots. So what's going on? Well, this little dip here, or this hill, is where I would be expecting to get my other 2 roots. But it's too high up. They're not down crossing the x-axis. So they don't appear as normal roots. Well, what are they? They are complex roots. This part of our function doesn't get to cross the x-axis. It never goes to y is equal to 0. So our other 2 roots, our other 2 potential roots are up here, and they don't cross the x-axis, so we would say that they would be non-real roots. They would be complex roots. And we remember back to our determinant and looking at complex roots before, when we were looking at quadratic equations, and we could use our discriminant to figure out if we ended up with complex roots. And in this case, we would end up with, we know we should get 3 roots. We would end up with 1 real root, x is equal to 2, and then 2 complex roots out of this area of the function here. In terms of finding enough information to draw this function, if we were asked to sketch it, in 6th year, as I said before, we're going to learn about how to find the bottoms of valleys and the tops of hills using our differentiation. So by the time 6th year is over, you'd know your y-intercept, you'd know your minimum point, your maximum point, and one of your roots. So you would be able to sketch this by the end of 6th year. But now going on to our main points for today, we're going to look at this function here. So we're looking at the third function down here. What do I notice about this function here? Well, I can see that I have a root at x is equal to -1. I can see that the y-intercept is 2, so 0, 2 is a point on my line. And here, my function is a tangent to the x-axis. It looks like it bounces off the x-axis. It just touches the x-axis at x is equal to 1. So what happens when I have my function a tangent to the x-axis? It means I have a repeated root. So let's write down the information I know about this function and see if I could get my equation here. So I'm switching back to my other screen, and I know that x is equal to -1 is a root, and I know that x is equal to 1 is a root, and I know that it's a repeated root, so I can write down x is equal to 1 as the third root. So I have all 3 of my roots for a cubic equation. And I also know that the point 0, 2 is on my line. Now from here, this proceeds exactly in the same way as the last question that we did. So y is equal to some constant, some multiple of the factors multiplied together. So I need my factors. So I rearrange this and I get x plus 1 is equal to 0. If I know this is a root, rearranging to make it equal to 0 gives me a factor. And I know that x -1 is equal to 0 is a factor, and x minus 1. So these are my 3 factors. So I have x plus 1 multiplied by x minus 1 to be squared. It's a repeated root, so I end up with the root. I end up with my factor squared because I have two of them. Now I'm just multiplying this out. We know how to multiply out these brackets, so when we do that, we are going to get x cubed minus x squared minus x plus 1. And now how am I going to find the value of k? Well, I'm going to sub in my x is 0, y is 2. And I'll find the value of k that way. So y is equal to 2, k is, we have 0 cubed minus 0 squared minus 0 plus 1. 2 is equal to k on 1. Therefore, k is equal to 2. So y is equal to 2 on x cubed minus x squared minus x plus 1. Y is equal to 2x cubed minus 2x squared minus 2x plus 2. Now, the final thing we want to talk about today, so we've been looking at cubic functions here, where we would expect to have 3 roots, just like with a quadratic, where we had a power of 2, we'd expect to get 2 roots. What happens if we have something that has even higher powers than x cubed? So I'm going to change back to GeoGebra. What happens if we get a function like this? Y is equal to x to the power of 4 minus 5x squared plus 4. This function here. Now, we're not expected to know very much about these functions, but as often happens in maths, if we understand what we've been doing, we should be able to extend it to a slightly new situation. If I was asked to find this function, my last equation here, if I was asked to find this equation based on this picture, or based on the roots that I was given and a y-intercept. So what would I do? I would look for the exact same thing as I did with my cubics. I would look for the roots, I would turn them into factors and multiply them out, and I would look for the y-intercept or some other point that they had given me on the graph in order to find the equation that I'm looking for. So all I would do, switching back, all I would do is say that x is equal to minus 2 is a root, x is equal to minus 1 is a root, x is equal to 1 is a root, and x is equal to 2 is a root, and I know that the point 0, 4 is my y-intercept. It is a point on my curve. I would turn all of these into factors, multiply them all out, and then use my point on my curve to find out what my constant would be. Exactly the same way as we have done it for our cubic functions. So there's nothing new there at all. It's exactly like our cubic and our quadratic equations have already worked out. So I think we should be all right with that. So that's what we need for being able to work with our graphs of cubic functions to find the equations or vice versa.